Hello students, I hope you are all well. I already discussed effect of Leavinggroup in nucleophilic substitution reaction or effect of Leavinggroup in organic reaction. Now I am going to discuss effect of solvent in nucleophilic substitution reaction. But before this, you need to know one parameter that is called dielectric constant. Dielectric constant. This parameter is very important in defining solvent polarity. And what is dielectric constant? It is a measure of a substance's ability to insulate charges from each other, and it is taken as a measure of solvent polarity. Okay, so this parameter taken as a measure of solvent polarity. Okay, so higher dielectric constant means solvent is polar, and lower dielectric constant means solvent is non-polar. But how we will categorize polar solvent and non-polar solvent? Solvent, if dielectric constant is greater than 20, then we can say that solvent is polar. If dielectric constant is less than 20, then solvent is considered as non-polar. And this non-polar solvent cannot stabilize cations or anions. But polar solvent can stabilize cation or anion. It can stabilize cation or anions. Okay, but again we can categorize polar solvent. How? So one is polar protic solvent, and another is polar aprotic solvent. What do you mean by polar protic solvent and polar aprotic solvent? Polar protic solvent is that the solvent which are polar but they are able to participate in hydrogen bonding network. Suppose, so these are H bond donor, polar protic solvent. And so examples: water, dielectric constant is nearly 78, methanol, where dielectric constant is 33. So see, H2 methanol, they can participate in hydrogen bonding. Or I think you already know. Okay, but in polar aprotic solvent, they are polar, but they cannot involve in hydrogen bonding network as they don't have the hydrogen donor atom. Okay, so for example, polar aprotic solvent is dimethyl sulfoxide. Abbreviation is DMSO, dimethyl sulfoxide. Dielectric constant is 49. Another polar examples of polar aprotic solvent is DMF. What is DMF? NN dimethyl. See, two methyl groups are attached to nitrogen. NN dimethyl formamide means there should be a amide group. So this is NCO, this is amide system. So NN dimethyl formamide. It is abbreviation is DMF. Here dielectric constant is 37. And I can give you, there are many non-polar examples of non-polar solvent like benzene, hexane. Okay, these are all a non-polar solvent. Okay, so now question is how this polarity of a solvent influence in nucleophilic substitution reaction. Changing the solvent in which the reaction is carried out usually has immense impact on its rate and may often result in a change in mechanistic pathway. Thus, during the solvolysis of alkyl halides by Sn1 method, we know in Sn1 pathway, first step is carbocation formation, and that is rate determining step. In Sn1 pathway, first step is carbocation formation. How carbocation forms? Because X differs from the substrate where X is Leavinggroup. Then you will get R plus and X minus, a ion pair. So we are getting a carbocation. So now transitions, this is the transition state where carbon and bond between carbon and X is going to break. This is transition state. Now this is in the intermediate. This is transition state. Just see that charge is going to be developed in the rate determining step because transition state is more polar than that of corresponding reactant. This is reactant. Reactant is neutral, but see, transition state is polar. So transition state is more polar than that of reactant. So we can say that transition state can be stabilized by polar solvent because polar molecules can stabilize polar system, polar substrate. Polar solvent can stabilize polar substrate. Clear? So yeah, I'm going to give you an example, then it will be more clear. Just try to consider in this on this example. Sn1 reaction of tertiary butyl bromide, that is if we do Sn1 reaction in 50% aqueous ethanol. Aqueous ethanol means water is present and water is more polar than ethanol. This is the product. Okay, suppose this is rate 1. If we do the same reaction in presence of only ethanol, absence of water, means solvent is ethanol only. This is the product. Then this is rate 2. It has been observed that rate 1 by rate 2 equal to 3 into 10 to the power 4. So rate 1 is found to be 3 into 10 to the power 4 times faster in 50% aqueous ethanol than ethanol alone. This one is more polar solvent than ethanol alone, because you know water is more polar, okay, than that of ethanol. So we can say that Sn1 reaction is preferred in polar solvent. This is very, very important concept. Sn1 reaction is preferred in polar solvent. Is that clear? And so solvation is very important in Sn1 reaction. As a result, Sn1 reactions are extremely uncommon in the gas phase where there is no solvent. So this statement is a kind of extra proof that Sn1 reaction requires polar solvent. Clear? Let's see what happens in case of Sn2 reaction. Try to concentrate on Sn2 reaction. This is nucleophile. This is the substrate. Nucleophile attacks the electrophilic carbon center. Leavinggroup leaves from the system. Then you will get, this is the transition state. This is the product. So for the Sn2 reaction on neutral substrate, because this is neutral substrate with a negatively charged nucleophile, however, increasing the solvent polarity is found not to alter the rate of the reaction significantly, and in fact there may be a slight decrease in the reaction rate. Strange. So Sn2 reaction doesn't prefer polar solvent. Like polar, I can say right now, okay, polar solvent, I should not say right now. Okay, suppose for this moment consider polar solvent. Okay, only polar solvent, because there are remind that there are two types of polar solvent. One is polar protic solvent and another is polar aprotic solvent. I am not right now, I am not going to say what happens in case of polar aprotic solvent. The here statement is true for polar protic solvent, and how I will discuss after some times. Yes, what I am going to say, increasing the solvent polarity is found not to alter the rate of reaction significantly, and in fact there may be a slight decrease in the reaction rate. Why? Because this is because the fact that in this particular example new charge is not generated and existing negative charge on nucleophile is more dispersed. See, here one unit negative charge, but in the transition state negative charge gets dispersed, it becomes delta negative. Okay, in the transition state compared to the starting material. Consequently, solvation of the transition state is expected to be somewhat less in comparison to that of nucleophile itself. So nucleophile is stabilized more. This reactant complex is stabilized more than that of transition state. So suppose this is where solvent polarity is less, reactant complex, energy of reactant complex. When solvent polarity is less, okay, then this is the transition state. When solvent polarity is less, this blue color indicates that solvent polarity is less. So this is the energy difference. But when, if we increase the solvent polarity, then reactant complex gets stabilized more and transition state is stabilized less. If it happens, see, the activation energy increases when you increase the solvent polarity. This is reactant complex. When solvent polarity is high. Transition state, when solvent polarity is high. So when solvent polarity is high, then activation energy increases than that of active synergy when solvent polarity is less. Okay, so that is why if you increase the solvent polarity, then in case of Sn2 reaction, rate of Sn2 reaction decreases to some extent. I think now it is clear. So solvent polarity doesn't prefer Sn2 pathway, rather it prefers Sn1 pathway. So there may be a changeover if you there may be a changeover uh, of mechanistic pathway from Sn2 to Sn1 if you increase the solvent polarity. So Sn2 to Sn1 wave if you increase the solvent polarity. Is that clear? I think now it is clear. Now we'll see another problem happens in Sn2 reaction if you increase the solvent polarity, or if solvent is polar protic solvent. So this is suppose if nucleophile, a hard nucleophile means nucleophile is small and there is 1 unit negative charge. If 1 unit negative charge exists in a small system, then charge density will be high. Okay, in that case, suppose if your solvent is water, then what happens? So it can make hydrogen bonding with water. It can make hydrogen bonding with water. So if nucleophile makes hydrogen bonding with solvent, then drastically the reactivity of nucleophile will decrease, because nucleophile is not naked, nucleophile is not bare, it is surrounded by water molecules. Then how it will attack to the electrophilic carbon center? I think you have understood. If nucleophile is strongly solvated, then there is a less probability that it will attack to the electrophilic carbon center. So Sn2 rate of Sn2 reaction will drastically fall. But in case of soft nucleophile like I minus, it is not going to make hydrogen bond with water because charge density on iodine is less compared to that of F minus or Cl minus. That is why F minus, Cl minus, Br minus, I minus, the reactivity increases. Reactivity increases. Reactivity of this nucleophile increases because I minus is not going to make hydrogen bonding with water. The probability is less because the negative charge density is very low. But another type of solvent we have, that is polar aprotic solvent. Polar aprotic solvent. What happens in case of polar aprotic solvent? Suppose it is dimethyl sulfoxide. Yes, this is dimethyl sulfoxide. I already have given one example, dimethyl sulfoxide, polar aprotic solvent. Just I am taking the canonical structure is S plus O minus. Okay. Now in such solvents, the cation is strongly solvated in the following way. If you take Ki, then there will be a K plus and I minus, where I minus is nucleophile. But what happens K plus? If K plus becomes if K plus is taken up by this solvent, then I minus will be free. Then reactivity of I minus means nucleophile will increase. So in this type of polar aprotic solvent, cation is strongly solvated in the following way. Suppose this is cation, electrostatic interaction. So cation is stabilized, or cation is surrounded by solvent molecule. So these solvents, they are lack of active hydrogen, and they cannot form hydrogen bond with anions, means hydrogen bond with nucleophiles. So this renders them ineffective for solvation of negatively charged ions, means here it is nucleophile. So the ions, means nucleophile, are therefore very weakly solvated in this media. So as a result, reactivity of anions increases enormously. In addition, the cation is solvated, so nucleophile, means anion, becomes free. So it is going to attack the electrophilic carbon. Okay, so there, so in case of polar aprotic solvent, M plus gets solvated. Result is nucleophile becomes free, means the reactivity of nucleophile will increase. In polar aprotic solvent, because their lack in active hydrogen, means they don't have hydrogen bond donor, then what will happen? Nucleophile will not uh, nucleophile will not be solvated by solvent molecules. So nucleophile cannot be solvated by solvent. Okay, so again, so that is why reactivity of nucleophile gets increases. Okay, so nucleophilic substitution of Sn2 type often occurs more rapidly in polar aprotic solvent. So Sn2 reaction is preferred in polar aprotic solvent. Is very important. Is that clear? So for today, I'm going to end my lecture here. Okay, bye.